Okay, so in this question, we've been presented with an unidentified compound, and we've been asked to work out the empirical formula of that particular compound. And we've been told it contains carbon, hydrogen, and oxygen, and the percentages by mass, as you see, are given in the question. Okay, so how am I gonna approach this? Well, the first thing I'm gonna do is I'm going to look at adding up the percentages that have been given in the question, and just having a look at what I get from that. So if we do that, let's do 40.68 plus 5.08 plus 54.24, right? So if you have a go at working that out, just have a look at what you get. And if you do have a go, what you should find is you get 100, right? Okay, so the next stage, what I'm going to do is I'm going to make an assumption to enable me to solve this problem. And the assumption I'm going to make is I'm going to assume that I've got a particular sample that's of 100 grams total, right? So I'm going to assume it's 100 grams total. Right, and when we make that assumption, because these percentage compositions, these are mass-based percentages, we can simply convert these and say, well, based on that, the carbon is 40.68 grams, right? And we can do effectively the same for the rest, right? So we can say the hydrogen, we've got 5.08 grams, right? And for the oxygen as well, you can say, okay, well, we've got 54.24 grams of oxygen. And what we're really trying to do in this question is to work out the simplest whole number ratio between the amount of the atoms of each element present, right? So working that out is not going to be done straightforwardly by keeping it in the format of mass. We want to convert it into a format where we can actually make an amount of substance to amount of substance comparison. And we know that the way of approaching that typically is going to be through moles, okay? So, and we know that moles N is equal to the mass in grams divided by the molar mass, right? In grams per mole. So in applying that to this question, we're going to take the molar masses of each of these elements, and we're going to divide the masses of each element by their respective molar masses. And so, well, what are the molar masses in these cases? Well, this can be worked out from the periodic table, right? So MR of, put that in brackets, MR of carbon, MR of hydrogen, MR of oxygen, right? Now I would assume you know the MR of hydrogen, probably of carbon as well, perhaps also of oxygen. But in any case, what I'm going to do at this stage is actually refer to the periodic table. So, which is just useful as a, I mean, for other elements you might need to actually refer to the periodic table. But here we can see for carbon it's 12. The relative atomic mass we see is 12. For hydrogen we can see it's 1. For oxygen we can see it's 16, right? And these are effectively the molar masses, right? So because we're looking literally at the atoms. So for carbon, as we just said, that's 12. Hydrogen 1. Oxygen 16. And now that we've got the molar masses of each of these, what we're going to do is we're going to effectively convert this using this equation we're going to convert these values, we're going to convert what we've got into molar amounts. So 40.68 divided by 12, 5.08 divided by 1, and then 54.24 divided by 16. Now when we work this out, what we can now do is we can effectively establish a molar ratio, right? So we can say whatever the moles of that, we're going to put them as ratios, compare them with each other like that. So I would invite you to have a go, see what you get when you work these out. Of course, for 5.08, it's you don't need a calculator to work that out, right? Because you're dividing it by 1, that's literally just 5.08. But for the others, you may find it useful to use a calculator. So for carbon, it's going to be 3.39. For oxygen, it's going to be 3.39. Okay, and so this is the molar ratios that we have now, and this setup is one that gets us much closer to working out the empirical formula, because now we actually have a comparison between the specific amounts of each element, right, without it being skewed by the different differences in the molar masses of the actual elements. Okay, so at this stage we're looking for integer values, right? We're looking for whole numbers, which we don't have at the moment. So the thing I'm going to do at this stage is I'm going to divide each of these numbers by the lowest number among them. And what we can see is that we've got equal lowest among the first one and the third one. So carbon and oxygen, they both have the lowest number of moles. So we're going to divide all of them by 3.39, okay? And this will help us to establish at least one whole number in our ratio. But of course, because we have two values being the same, it's going to establish actually two whole numbers, right? So obviously we don't need a calculator to work that out, that these are 1. But if you then have a go to see what you get when you calculate this, what you should get is $1.49853, and then well, we do have, now we've got two whole numbers, but for hydrogen, we still don't have a whole number, right? Which is an issue. And but what we can do is we can do some scaling. So we can effectively multiply the hydrogen by increasing numbers from 2, 3, 4, 5, etc. until we get to a whole number. And the first number that actually works along that gradually increasing scale of whole number multiples is the one we're going to focus on. Okay, so in this case it's quite straightforward. So when we multiply all of these numbers by 2, remember we have to do, if we're going to multiply the middle number by 2, we're going to need to do that same operation with all of them. So 1 is also going to need to be multiplied by 2, and 2 is the first number in this sequence, right? So if you do that, what you're going to get is 2, and then you're going to get 2.99706, and of course that's going to have to be 2, well, that should be a 2. We're going to have 2 at the end, right? Okay, so now at this stage, if you take a look at what we get if we actually round the middle number to 2 decimal places, 2 decimal places, we're going to get 3, aren't we? We're going to get 3.00. And if we round it, of course, even to 1 decimal place as well, of course, we get the same. We get 3.0, right? And this basically indicates to us that the number is so close to being 3 that we can actually assume, for the purpose of what we're working out, the empirical formula, we can assume that the number is 3, and we round it to 3. And therefore, once we've done that rounding process, we get 2, 3, 2, right? Now, do we now have the simplest whole number ratio between the numbers? Yes, we do. We now have the simplest whole number ratio. And so we can effectively say, okay, well, when we actually write this out as a formula for CHO, we can, C is going to have a 2 associated, H is going to have a 3 associated, and oxygen is going to have a 2 associated. And so if we now write this out, we're going to get C2H3O2. Okay, and this is, in this case, our empirical formula.